This is the sole mini-lecture for section 2.2 of the textbook, which corresponds to section 1.2 of the syllabus. Recall that in the last section we talked about sets, which are groups of objects. And our main interest in talking about sets at this point is really so that we can understand counting. And when we learn how to count, we learn how to count objects. So we just really wanted to understand objects. Now we want to understand the process of counting. And it can be a little difficult to do that because you're so used to it. So let's imagine a thought experiment. Imagine that you're a shepherd living in prehistoric times. You have a large number of sheep. You have, maybe 100 or 200 or something like that. At any rate, it's too many to be able to tell at a glance how many there are. Every morning you let them out of the fold into the pasture, and then every evening you let them back in. One day you start to worry that you're losing sheep during the day. Maybe they're getting lost or stolen by someone, or maybe wild animals are eating them. So this is prehistoric times, and no one has invented a system for counting yet. In our culture, we use the base 10 numeration system, which was invented in India maybe 1,000 or 2,000 years ago. But they didn't have anything like that back in prehistoric times. They maybe didn't even have names for the numbers past a certain point. They had no system for naming numbers. So the question is, how could you keep track of your sheep without being able to count them? One idea would be to collect a heap of pebbles and a basket. As the sheep leave in the morning, you would place one pebble in the basket for each sheep that passes out through the gate. So for each sheep that goes through the gate, you put a pebble in the basket. Once all the sheep are out into the pasture, you have exactly as many pebbles in the basket as you have sheep in the pasture. And you know that with certainty, but without having been able to count them, without even knowing what counting is, perhaps. So the basket of pebbles is like a model for the herd of sheep. Each sheep has a pebble, and each pebble has a sheep. Then in the evening, you remove one pebble from the basket for each sheep that returns. If you have any pebbles left over, then you must have lost some sheep. A one-to-one correspondence between two sets is a pairing between the sets that leaves nothing out and uses nothing more than once. For example, we had a one-to-one correspondence between our basket of pebbles and our herd of sheep. So imagine, here in this loop, this is going to be our basket of pebbles. And I'll draw 7, although, we're imagining that we are not able to count them. And then here's our herd of sheep. And as the sheep passed out in the morning, we paired one pebble off with each sheep. So each sheep gets a pebble, each pebble gets a sheep, and there's nothing left out or used more than once. Okay, that is what we call a one-to-one correspondence. If you've ever watched a small child playing, let's say maybe a 3 or 4-year-old, you often see them do things like pair objects off or maybe line them up. So for example, you might observe a child, putting dolls around the dining room table. Okay, each chair gets a doll and each doll gets a chair. This is something I've watched my own kids do, and you can see sometimes it doesn't match up, and then you can tell that bothers them a little bit. Maybe a couple dolls will have to share a chair, or maybe they'll have to go find someone to fill up an empty chair. But you know that you can tell that their idea is for each doll to get its own chair, and for each chair to have its own doll. So what they're doing is playing with the idea of a one-to-one correspondence. You can also see children, line things up like their cars, perhaps, or maybe each of their army guys gets a gun or something like that. Um, when you watch them playing like that, you're watching a precursor to counting. Okay, this is one of the steps that a child gets to before they learn how to count. And really, in a way, they are counting, even though they haven't learned the numbers yet. Okay, so when you have a one-to-one correspondence between two sets, you say that they're equivalent, and you express that with this little squiggle symbol. So we don't say that they're equal, we say that they're equivalent. You can pair them off. In effect, we're saying that they have the same size, but notice that we haven't talked about numbers yet. Now, the set of natural numbers is the set 1, 2, 3, 4, and so on, forever and ever. Now, what are the natural numbers? Well, at this point, you can think of them this way. They are just a list of words that stay in a certain order, and that's all there is to them. It's just a list of words that you memorize that have a certain order. And they keep going and going. And at this point, for us, that's all there is to the numbers. And when you first teach a child how to count, quote unquote, you are teaching them how to list those words. Okay, they may not really know what to do with them, but they can list them. Now, when we count a group of objects, what we're doing is we're establishing a one-to-one correspondence between a set of objects and the set of numbers of the form 1 through k, where k is a natural number. So imagine, you have a bunch of students on a field trip, and you're trying to make sure you've got them all on the bus, and you count them to make sure of that. What do you do when you count them? You can't just look at them and tell if they're all there. You might know them all, but you can't just tell at a glance whether they're all there. No one can do that. Your brain can't handle it. What you do is you point to each of them in turn, or at least look at them, and either say out loud or mentally say a number. So you point at each of them in turn and you say a number. When you do that, you are establishing a one-to-one correspondence between a list of numbers and a set of objects. So basically, the numbers are serving as your pebbles. They're pebbles in your mind. So if we have our herd of sheep, we draw our 7 sheep again. But remember, we're not supposed to know it's 7 yet. And we're going to pair those off with a list of numbers. Okay, and I'm pretending I don't know the size yet, so I'll write the numbers one at a time. Okay, so that's 1, 2, 3, 4, 5, 6, and 7. Okay, so we paired our sheep off with that list of numbers. Okay, that is the counting process. So the numbers are playing the role of the pebbles. They're like pebbles in your mind. Now, a set is said to be finite if it's either the empty set or it's equivalent to a list of numbers 1 through k. So basically, we're just saying that it's a set that you can count. If you start assigning numbers to the elements of the set, eventually you will run out of elements. And that largest number that you get to is what we call the cardinality. Okay, that's an important word to know, but it's easy. Okay, the word cardinality just refers to how large the set is, or in other words, what is the largest number you get to in the counting process. And you write n of a equals k. So for example, in our herd of sheep, let's call this set S for sheep. And then we showed that S was equivalent to the set of numbers 1, 2, 3, 4, 5, 6, and 7. So that means that 7 is the k, so to speak, and therefore the cardinality of S is equal to 7. So we don't say that S is 7. It's not. S is a bunch of sheep. S is not 7. Its cardinality is 7. And we write the cardinality like that. The number of sheep is 7. Okay, now the cardinality of the empty set is the number that we define as 0. So that's the definition of 0. It's the cardinality of the empty set. And if A is not finite, then it is said to be infinite. So an infinite set is a set that you would never come to the end of in your counting process. Okay, but what you should notice here, and this will come up on the homework, is that all of the ideas we've talked about so far, like equivalence of sets and one-to-one correspondences, those all apply equally well to infinite sets. Now, one last thing remains to be discussed, which is the greater than less than relation. So let's imagine that we're the shepherd again. You have a neighbor who owns their own herd of sheep, and you want to decide who has more sheep. How can you do that without counting? So one idea would be to pair the sheep off. Whoever runs out, that should be first, sorry, has fewer sheep. So, yeah, maybe my herd has 4 sheep. Let's say this is the neighbor's herd. Okay, and let me not use the letter N for that. We'll call it H for herd. And then let's say, here's my sheep, and I still have my 7. Although, again, I'm not able to count them per se. Okay, and so we try to pair them off. These pair off, and these two, and these two. Okay, but you see, he ran out before I did. I still have 3 that are left over. And that means that I have more. So what we've done here is we've paired the neighbor's sheep off with what we call a proper subset. Remember that from the last section. A proper subset of my herd of sheep. So if A and B are finite sets, where little a is the cardinality of big A, and little b is the cardinality of big B, then A is less than B if the set A is equivalent to a proper subset of the set B. So in my picture here, the cardinality of H is 4, the cardinality of S is 7, and what this establishes is that 4 is less than 7. Now, last but not least, here's the homework. As usual, it might be a little more abstract and open-ended than you're used to, but do your best on it, and we will discuss it in class.